floor is yours.
Okay. Good morning, everyone. My name is Jiany Samara. I will be presenting today our research on behalf of myself and my colleagues, as well as my research supervisor, Professor Hiam Khoury. Our research is entitled A Three-Layer Taxonomy and Predictive Digital Twin for Role-Aware Human-Robot Collaboration in 3D Concrete Printing. Now, here is the outline of our presentation for today, and then let's dive directly into the main topic. What is 3D concrete printing, and why is it important to take care of the safety measures revolving around it? 3DCP is moving faster than its safety frameworks. The main challenge is that it's a large robotic system, open and changing workspaces, and continuous material disposition. We also have multiple workers with different roles that interact with such machines, evolving with partially built structures that aren't quite safe and as stable as we would like. Now, in this field, what we have seen till now is that the general standards are not enough to take care of such a non-static machine. For example, some focus on additive construction qualifications, but exclude environmental, health, and safety aspects of robotic operations, whereas others address industrial robot safety and collaborative applications, but are mainly based on fixed cell industrial robot assumptions. Hence, 3DCP requires a specific safety framework that accounts for the human, the robot, and the construction site all coupled into one system. And so just to come back onto all of these points, whereas a conventional collaborative robotics, we have fixed workspaces, a stationary or localized robot cell, a single main operator, interruptible operations, and localized robot hazards. 3DCP, it's a large gantry or construction scale robot in an open and evolving construction sites, continuous concrete deposition, multiple worker layers, and a partially built structure that changes over time. It is in that spirit that we have started our research. Our main aim and contribution was to create this framework. Our research is still till now a framework with a small experiment at its core and is yet to have been truly concretized. But in this framework, we have three main contributions. First, the human layer. The human layer with wearables, sensors, etc. The robot layer and the site layer. Second contribution is the slide view predictive digital twin with short horizon forecasting and machine learning. And the third and final contribution is the use of 7 role-aware interaction patterns aligned with collaborative robot safety concepts in order to take into account the different uses of such machines and how they would affect the interaction between the human and the robot in our equations. So, to dive deeper into each of these components, first the three-layer taxonomy. The proposed taxonomy organizes the 3DCP collaborative environment into 3 connected layers. The human layer that captures worker state, including physiological, spatial, kinematic, task, role, and psychological indicators. Second, the robot layer, capturing gantry motion, process state, extrusion behavior, configurations, topic constraint, and the distances between human and robots. And finally, site layer with partially built structures, workspace geometry, environmental conditions, and workflow schedule. They are all used in our model in order to make the best predictions. These predictions here are used in the digital twin that we have created using these 3 layers. It then performs a short horizon forward simulation of worker trajectories, robot motions, and process states that might be happening. And we will come back a little bit later on the specific details of this machine learning model. The main point is that the supervisory decision cycle updates every 5 seconds for new predictions with a primary horizon of 5 seconds and the secondary one of 30 seconds that is still in the works. And finally, component 3, the 7 role-aware interaction patterns. As we have said, there are multiple roles and multiple states of the 3D concrete printing machine. The console monitoring, acute operator load, in envelope intervention, etc., etc. Each pattern combines worker role, triggering state, digital twin response, and ISO 102.18 collaborative mode. And here is an example of a scenario and feasibility check. As we can see, a labor worker enters the print envelope during a scheduled interlayer pause, so stage 3. There are the multiple parts of the machine, the digital twins response. The system identifies the worker role and workflow state, then selects pattern 3 in envelope intervention. If the process degradation is predicted, which is pattern 5 when the machine is about to stop, pattern 5 may supersede pattern 3, allowing a graceful transition before stopping. And the human layer feasibility check, a proxy evaluation was conducted using the WESAD datasets for binary stress classification. And we come then to it. For the human layer machine learning feasibility check, we used 2 models till now. First, as a baseline, we have used the XGBoost with 60 input mean pooled for every prediction, and have seen some quite good results as a baseline. But what we wanted to work on more, and something that we haven't seen yet in this field, are models such as the temporal fusion transformer that would use attention in order to better understand what is happening on the construction site and make better predictions. For the TFT model, it doesn't take an average of the past 60 data. It analyzes them through time to see its evolution. And what we can see is that TFT outperforms the XGBoost, but the main point that we can also see is that it outperforms it with profiles on. Now, to come back to our profiles, the profiling in this research is when we attribute to workers certain characteristics. For now, it's only their normal average, for example, heartbeat, average blood pressure, etc., so that we can normalize the data and see better the differences between them. But in the future, it could also be the workers' roles and positioning. It could also be their experience, etc., to really be specific to each and every one of them. We used the WESAD dataset till now in order to run these tests, and are working on creating our own dataset in a controlled environment. The human layer pipeline is thus feasible. TFT performs best when worker calibration profiles are included, supporting the need for personalized role-aware safety modeling. And so, in conclusion, what we can mainly take away from this is that safe HRC in 3D concrete printing requires integrating worker state, robot process state, and site evolution. It's not only one of them, it has to be the 3. The limitations till now is that the framework has not yet been validated as a fully deployed 3DCP system, and our future work would focus on that, on validating the 3DCP platform, on testing false positives and false negatives under scripted hazard scenarios, developing automatic inferences, and formalizing interaction patterns for future standardization work. We can see that this framework has a lot of potential, and maybe one day we could even integrate it into a construction site where all workers would just only need to have like a Fitbit, a Whoop on them, some small sensors, and we could greatly improve the safety of all workers when it comes to their interaction with 3D concrete printing. Thank you.